stats to speak about the new developments in the phosphorus index. And of course, I'm going to start out by saying we're still working on the P index. We're still making some adjustments. It's a continual process. I don't know what that means in regards to the regulatory playing field as far as MDA. Some of the people who are on the call from MDA can probably at the end comment. I know that question will come up. But we are still working through this. So first I want to start in with some basics, some fundamentals, why we use the P index, just as a refresher. I'm sure many of you are familiar with this, but I think one of the key components is that phosphorus is not like nitrogen. Now, it may sound simple, but I think we forget that a lot in this conversation. Most importantly, probably less than 15% of the applied phosphorus is available in the first year, especially in low soils, maybe even less than that. I've seen numbers that range from 5 to 20% availability in applied phosphorus. So one of the interesting things about phosphorus as opposed to nitrogen is reductions in rate will not improve efficiency. And that's efficiency calculated as the percentage of fertilizer that gets into the harvested portion of the crop, a partial efficiency or however you wish to define it. And that's a key point to make, that phosphorus efficiency isn't directly related to rate as it is with nitrogen. And this is the same with all immobile nutrients like phosphorus. So increases in efficiency will not result necessarily in decreases in loss over the long term, but definitely not in the short term, because the factors that control loss are not the factors that control crop uptake and efficiency. So the main way to decrease loss is through management of timing and placement, and how the phosphorus that is there is exposed to transport pathways, not necessarily how the phosphorus is exposed to crop uptake. So I would say, to summarize that, there's a dubious if non-existent relationship between P use efficiency and P loss, and I think sometimes that gets lost in the discussion. And it's very different than the situation with nitrogen, where application in excess of crop utilization is nitrogen that is at risk for loss. This is not the case with phosphorus. Why phosphorus management? I think everyone should be very well aware of this, but it's essential to all forms of life on Earth. It doesn't have any known toxic effects, and that history is what's brought us to the point where it's become an environmental concern. Previously we thought, well, it's immobile, it doesn't have these toxic issues. If you over-apply nitrogen, you can damage your crop. But not phosphorus. So, historically we bankrolled phosphorus for future years through over-application. You do need adequate levels of phosphorus in the soil for crop production, but unfortunately it's also usually the limiting nutrient in fresh water as far as eutrophication, algae growth, and negative water quality impacts. P impacts on crop production: vigorous crop growth, improved resource utilization as far as water and nutrients. So that has some positive environmental implications. If you're short on phosphorus, you have poor growth, poor soil cover. Better resistance to stress, disease, pest, moisture, and temperature. A lot of this comes because sometimes we see early maturity. In corn production we'll see earlier silking, and that can help with early maturity, can help with pollination and some other things, and resistance to the drought that we often see that time of year here. So very important nutrient. Soil pH, I would say, is one of the things that dominates phosphorus availability and therefore phosphorus efficiency. Often when I get called out to look at a phosphorus deficiency, there's plenty of phosphorus in the soil, but in localized areas in the field, say an eroded area where you have coarser textured soils, more acidic, low pH, and the phosphorus isn't available. So you have plenty of phosphorus in the soil, it's just not available to the crop. So phosphorus, soil pH management is very important as far as managing phosphorus availability and phosphorus efficiency. And that has to do with this figure that shows at what pH which minerals in the soil are responsible for phosphorus fixation. And our soils tend to be on the acidic side, and in that pH range of around 5, iron and aluminum oxides dominate phosphorus fixation. As your pH goes up, the calcium phosphates begin to dominate the processes in the soil. So the factors that influence P availability to crops and mobility through the soils. P moves from soil solids to plant roots through diffusion. This is a process that occurs over short distances, probably less than a quarter inch. And so plant roots can only obtain the phosphorus that's in close proximity to them. Dry soils, cool soils, these things can reduce diffusion. So early in the season, even if there's enough phosphorus in the soil, we find that application of phosphorus close to the seed in a starter band can really increase early growth. Even if we don't see a yield benefit, we'll see an early growth benefit just because of this diffusion issue. As far as transport, it basically comes down to this. You have phosphorus sources. Either you can transport phosphorus directly from fertilizer and manure applications, or phosphorus that's tied to the soil through erosion. That's probably the worldwide dominant pathway for phosphorus transport, is attached to soil particles and through erosion. That's why soil conservation is so important in regards to phosphorus. But we can also transport phosphorus in runoff as dissolved phosphorus. Even if soil particles are not moving, we can directly dissolve it from a soil that is saturated or from surface applied manure. So you basically are dissolving that very soluble phosphorus in the manure that's laying on the surface, or from a high P soil. Often we get phosphorus stratification in no-till soils from repeated applications at the surface, and that soluble P can be transported in runoff. Or in some very limited geographies, phosphorus transport, for example, the lower eastern shore of Maryland, is dominated by subsurface flow. This image doesn't really capture what's happening, but it's an approximation. If you have a saturated soil close to the surface and you have shallow subsurface flow, say to a ditch, and again this dominates on the lower eastern shore, 90% of your phosphorus could be moving through that pathway as opposed to surface pathways. And traditionally we focus on the surface pathways because 99% of the world, that's how phosphorus moves. But in these areas, either with tile drainage, it can be an issue if you have saturated soils, but more so in ditch-drained areas, you get these shallow subsurface flows of phosphorus. So again, surface flow tends to dominate our discussion when we talk about phosphorus. Dissolved P is 100% biologically available, so while you may move fewer pounds per acre of dissolved P, those pounds have a larger impact immediately on surface water because it's immediately available for algal uptake, and that's what we're worried about. Particulate P carried on the eroded particles is not immediately available, but it can be processed in the water column and become available, so we still need to manage it. Leaching and lateral subsurface flow in these limited situations that I described, but typically leaching is very minimal. In other words, leaching is deep flows of phosphorus into groundwater. That's still very limited, and this lateral subsurface flow is a little bit different because you're not hitting groundwater, you're just moving it directly to a ditch or through a tile drain in kind of shallow subsurface flow. And these become to be issues when the soil is saturated with P. And dissolved surface runoff, again, when soil is saturated with P. And I'll talk about this throughout because this is really a component that we've added to the new P index that wasn't there before. Evaluating this soil saturation. The soil really is like a cup. It has a lot of capacity to hold P, but eventually you can fill that cup up. The size of your cup in this area is determined by the amount of iron and aluminum in the soil. So we'll get into that later. Sources or types of particulate P in runoff: soil organic matter, mineral P. In cultivated land, particulate P is probably 75 to 90% of the total P load. In no-till or pastures, particulate P is probably less than 50% of the total P. And bioavailable P has a wide range in particulate P. It can be 10 to 90%. If your particulate P is organic material, like manure, that's running directly off the surface, then it's going to become bioavailable pretty quickly. But if it's mineral P tied to iron and aluminum minerals, it can take a long time for it to become bioavailable. Dissolved phosphorus in runoff. comes from the soil solution. In saturated soils and cultivated land, it's much less because we get better soil to phosphorus contact. But in no-till, where we have stratification of phosphorus, the dissolved P can dominate, especially if you're applying nutrients on the surface and not injecting them, and the bioavailability is 100%. So how much P is lost? Usually less than 5% of applied P is lost. And this is an important point conceptually because, as we manage our phosphorus, we think, well, typically with nitrogen, we think if we manage our losses, it's good for our bottom line. But really, the amounts of phosphorus that can impact a water body are as low as 0.1 or 0.01 parts per million in the water column. There's some debate over the exact threshold number, but in cold water areas, that number is much lower. And those very small concentrations in water can have a huge environmental impact, but not an economic impact on the farmer per se. As little as 1 to 3 pounds per acre loss is really minor. You wouldn't see it in your soil test. You wouldn't see your soil test going down because of your phosphorus loss, but it would have a huge impact on the environment. So really, environmentally significant losses of phosphorus are not economically significant. So I want to show a couple case studies that help to inform the process of creating the new P index. These aren't all of them, but these are just kind of examples that were very clear. The first is we want to talk about hydrology and transport versus source. And when we talk about source, we talk about the applied fertilizer, manure, biosolids, compost, and the phosphorus in the soil, and versus the transport mechanism. So in this case study, it was published by Tony Buda, who works for USDA ARS up in State College, Pennsylvania. They had a watershed in central Pennsylvania where for about 5 years they were measuring runoff. During natural storm events, it was a strip-cropped sloping field, so it was separated into 3 separate fields going up the hill. The upper 2 fields had what would be considered above optimum soil test phosphorus, roughly equivalent to our fertility index values we use here in Maryland of 144 and 177 parts per million Malic 3 soil phosphorus. And these fields were receiving manure and starter fertilizer. The field closest to the stream was kept in a grass buffer because of its landscape position being close to the stream. No phosphorus was applied, and as a result, we saw a lower soil test P. It's still up there in the range. It's not low per se, but 78 parts per million Malic 3 soil phosphorus. So if we just use the soil test to decide where I applied my manure, assuming that I'm a dairy farmer and I have manure I have to get rid of, and the regulation was based on soil tests, I would apply it down here in this field because they had the lowest soil test. And these two are considered, 150 is the trip value here in Maryland where you have to run a P index. So this field would be really close, and this one you would have to run a P index to apply manure. This one you would not. So if we were just using soil test P, we'd come in here with our manure. Well, what we actually saw were that in these 3 different fields, we had 8 kilograms per hectare per year phosphorus runoff load. That's really high. 1 kilogram per hectare per year of runoff load, which is still environmentally significant. And then the field with the highest soil test P actually had the lowest runoff load, less than 1 kilogram per hectare per year, barely measurable, not necessarily environmentally significant. So what was going on? Well, we look at the runoff volume from each of those fields. And you can see that the runoff volume from the lowest field at the bottom of the hill with the lowest soil test P was significantly greater. Hardly any water was leaving the top field. So, from this we can clearly see that if the water is not moving, as is the case here, the phosphorus does not move. The lowest field was a riparian zone. It was prone to water logging, and runoff volumes were 46 times greater than from the other 2 fields combined. So it's significant water movement from the lowest field with the lowest soil test P. 27% of the runoff from the upper 2 fields re-infiltrated before reaching the stream. And as it re-infiltrated, obviously that phosphorus would have been removed by the iron and aluminum minerals in the soil and not reached the surface water. So if we use just the soil P threshold and said we're going to cut off manure application above 150, this farmer would have applied his manure here and done significantly greater environmental harm. So that's the reason we use a P index. Here's some of our data that we're working on publishing now. This is from 2006 at the Y Research Center, a runoff study. We had no-till, turbo-till, strip-till, and chisel plow. The entire field was applied with about 4 tons per acre manure. The soil test was 65 parts per million, so nowhere near our environmental threshold again. But we see that the total phosphorus load lost in that year was about 4 pounds per acre in 2006 from the no-till area. Here's the residue, percent residue cover. So, typically we think, well, no-till is good for controlling phosphorus loss because we're controlling the particulate P loss. Well, what we have here is direct dissolution and movement of phosphorus from the no-till field because that manure was laying on the surface. Even a little bit of tillage with the turbo-till reduced the phosphorus load about 20% because we got better manure-to-soil contact, reducing that dissolved phosphorus load. So this is a example of how management overrode phosphorus source, both from the soil, which had a low source, or the manure, which was a higher source. The management was able to control that load. By going to complete conventional tillage with a chisel disc, we really significantly reduced the phosphorus loading from that field. Ditch drain systems, again, present another challenge. Here in this ditch, what you see here is a pipe coming out from an agri-drain. There's a primary ditch up here to the left. It's draining the field into this ditch. We have extensive ditching here in Maryland. We have some areas on the lower eastern shore with historic over-application of phosphorus because we applied poultry litter at nitrogen-based rates, well in excess of crop removal rates. Over the course of 50 years, we have elevated soil test P and soil phosphorus saturation. So now we have a situation where the top anywhere from 6 to 24 inches of the soil is completely saturated in regards to phosphorus. And any water that moves through that soil desorbs phosphorus and moves it through shallow subsurface pathways directly to these ditches. Here's some data from USDA ARS, Pete Kleiman up in State College, Pennsylvania. This research was conducted at University of Maryland Eastern Shore in Prince Suzanne. 3 years, we have this left chart shows the flow in cubic meters per hectare coming, light blue bars are from the field, and dark blue bars are the ditch that drains that field, what the flow was in the ditch. And we can see there's a tremendous amount of water going down that ditch each year that didn't travel across the surface of the field. Surface runoff accounted for only 3 to 9% of annual ditch flow. So that means greater than 90% of the water in the ditch was traveling through subsurface pathways, and nutrients move with the water. So when we look at the total phosphorus going down the ditch in kilograms per hectare per year, ditch phosphorus loads were extremely high. In 2003, we lost 40 kilograms per hectare. That is one of the highest phosphorus loading rates I've ever seen. And the surface runoff from the field only accounted for 5 to 22% of the annual ditch export. So 80 to 95% of the phosphorus traveled through subsurface pathways with the water that was traveling through subsurface pathways. So another concern we have, this is the same data set for the year 2003 from that field. Do incidental transfers from fields contribute to dissolved P in ditches? What we see are these black dots are concentrations in runoff, surface runoff across the field. Manure was applied in early May, and we see that concentrations are highest right after application, and this is in the surface runoff. So, those rainfall events right after application, we had high P concentrations, and then as the phosphorus sorbed to the soil, the concentrations in runoff significantly decreased. However, if we looked at the concentrations in the ditch, these red dots, they are not related to that manure application. So this ditch drains that field. The Black dots are the concentration in the surface runoff. Red dots are the concentration in the ditch. The ditch concentration is not affected by that single application. So what we see in the ditch is a slow bleed, and like this high point right here, this outlier, it's probably a large storm event with high flow rates through the ditch, and we'll see higher concentrations in those kind of events because we detach soil particles and algae mats that are in the ditch with real high flow rates through those ditches, and then the sampler will grab that algae and detritus that's moving down the ditch in those high flow rates. But in general, the hydrology of the system, we get a slow bleed of phosphorus from that field, and we really can't see what's happening up on the field in regards to application in the ditch. So we've got to control that slow bleed. Another thing, here's some data from Dr. Crowderville and Dr. Cole, unpublished as of yet. I've averaged this across a number of sites, and what they did was back between 1994 and 1997, in these treatments here, the blue, yellow, black, and red, they used manure applications, different rates of manure every year, to raise the soil test P. So on the y-axis here, we're looking at soil test P. And then they stopped applying phosphorus and just cropped it out with crop rotations. And we see that you can rapidly, with manure, raise soil test P. In the first, after application ceased, in the first, they waited, looks like about 3 or 4 years before the first sampling. And we see the soil sorption that occurred over that time, and then it's a slow drawdown. It takes a very long time to draw down high soil P. Especially look at the one where they brought soil test P up above 500. That slope of that line is very flat. We see kind of a drop off here, and then it comes back up. There's two things happening there. One is soil pH was declining because it hadn't been limed in a while, and when we lime it, the phosphorus becomes more available. But also they switched labs, and so you can see a little fluctuation when they switched labs. But we're still sampling these fields, and these higher soil test P field, the red one, those plots that received the most phosphorus have really flattened out. So we're having a lot of trouble drawing down those fields. They started down around 100 parts per million, 100 FIV, soil test P. And, you know, as we model this outward, it looks like it would take 50 years to bring that back down into a reasonable range. So if you think back to this slide, that we have a slow bleed that's related to the soil being saturated with regards to phosphorus, that slow bleed can occur for many, many years, even after phosphorus applications cease, as is the case with this data. So going on some information like this, using studies like this, our objectives with revising the phosphorus index were to accurately assess relative risk of P transport and have a tool that was broadly applicable across all the various physiographic provinces in Maryland, the Piedmont, the Mountain, the Coastal Plain. We wanted to include some of the new science, specifically regarding P transport, that was coming out about ditch-drained areas on the Lower Eastern Shore. And we wanted to increase emphasis on management decisions, because these management decisions are what we can use to decrease phosphorus losses. So one of the major changes found in the current draft that's out, I believe still for public comment, first it's the new name, the University of Maryland Phosphorus Management Tool. This was really semantics to some extent, but you know, the phosphorus index, what does that really mean? We really want a tool that helps the end user manage their phosphorus, so we named it as such. Second, we eliminated the very high category and went to 3 interpretive categories. This was mainly a policy decision. The new federal guidance from NRCS for the 590 standard said you had to have at least 3 categories, and we could have gone with 4 according to the NRCS, but within circles in Maryland, policy circles, there were a lot of people asking, well, what does very high mean? If you're high, you're high. Anything beyond that is still high. So we eliminated the very high category. And we removed some of the recommendations. The old P-index, if you'll remember, if you were low, it said in there you could use N-based management. We removed it. This is a phosphorus management tool. We want the recommendations to come out of to all be couched in terms of phosphorus management. And then there are three major, this is the big change. The three major transport pathways were separated arithmetically. And we'll go into this in more detail, but before we just had a transport side and a source side, and we had components for surface, subsurface, leaching, particulate P. But they were all grouped together, so you ended up with an average of the transport risk from those three pathways. We separated them out, so in effect we almost have three separate phosphorus indexes that are then summed to give you your cumulative risk from those three different pathways. And I see that Joe Mercer has commented that the public comment period on the PMT closed at the end of February, so the public comment period is over. So here's the old interpretive categories: low, medium, high, and very high. Everyone should be familiar with those. I'm not going to go through those in great detail. But basically, if you were low, you could use N-based planning. If you were medium, you could use P-based planning N-based planning 1 out of 3 years. If you scored high, it was P-based planning every year. And if you were very high, no phosphorus application. With P-based planning, basically referring to the amount recommended by soil tests or based on crop removal. Here are the new interpretive categories. Low is 0 to 50. It's a low potential for P movement from the site, given current management practices and site characteristics. Soil P levels and P loss potential may increase in the future due to continued nitrogen-based nutrient management planning. So total phosphorus application should be limited to no more than a 3-year crop removal rate applied over a 3-year period. So we've allowed that 3-year crop removal, but we allow it in one application, a single application, your 3-year crop removal rate. And I'm going to show some examples of this in a second. For the medium interpretation, the potential for P movement from the site is considered medium potential. Practice should be implemented to reduce P losses by surface, subsurface, and erosion. You can look at your P index score to figure out what your risk factor is, and that will help you decide which management practices to put in place. The phosphorus-based nutrient management plan should be used for this site. And so that's the same as high under the old interpretive category of using soil tests or crop removal. So over a 3-year period, you would apply the same amount as up here, for example, if you were doing continuous corn. But each individual application is lower. And so that way we reduce the potential for incidental transfer, because incidental transfer, in other words, what's lost in the rainfall event through surface runoff immediately after an application of, for example, poultry litter, is rate dependent to some extent. So we've limited how much you can apply at any given time. And then high is the same as the old very high, greater than 100, no phosphorus application. Does this mean that 150 criteria has been removed? No, I didn't say that. The 150 criteria, as far as I know, is still in place. That's a question for Joe Mercer, perhaps, but as far as I know, MDA is still choosing to use 150 as the threshold point for running a P index. This score here, 100, is your P index score, not your soil test value. So, how will this impact farmers? If your score before was 0 to 50, N-based planting, now 3-year P removal. And we look down here, assuming a continuous corn with a yield goal of 150 bushels per acre, poultry litter testing 60-60-40 in pounds per ton. These are just rough estimations as an example that I threw out here. Under the old process, you could have applied 5 tons per acre. Under the new one, 4.5 tons per acre. And then you've got to still default to your nitrogen-based plan as well. So, you know, depending on what your nitrogen rate is, that may or may not, you may have to go lower. So not a big change. Under medium, the old way, P-based planting 1 out of 3 years. N-based planting 1 out of 3 years. That's a typo there. You would have had 5, 1.5, 1.5. And under the new one, it's just P-based planting, so 1.5 tons per acre. And then P-based planting under the old index, and under the old and new, that's the same. And then, again, the same here if you score over 100. I'm not sure I understand Kathy's question. So the old PSI, we had Part A times Part B, if you'll remember. And Part A was your transport characteristics: Russell, runoff, leaching, subsurface drainage, dishes to water, and the watershed. And the Part B, you had soil test P, P fertilizer rate and solubility and method of application, and organic P rate, solubility, and method of application. So due to the multiplicative nature of this, where you took all these factors and added them up and multiplied them times these factors, you needed a high transport side and a high source side to get a high score, and this defines the critical source area concept. I'll give a little more detail on that later. But the problem with this was that transport pathways were summed. See, on this Part A, we summed particulate P, surface dissolved P, subsurface dissolved P. They were all kind of summed together. And so if one pathway dominated, like on the Eastern Shore where subsurface loss dominates, the others would water down that transport component, so to speak. And management was really kind of mixed in the background: distance to water, your application method and rate were mixed in. They didn't come out as clearly. And we used the same source for all the transport pathways. So your source was all added up over here and multiplied times all the transport pathways. But really, soil test P is not the soil source for necessary, or not the most accurate way to measure the source that's feeding subsurface drainage. So we changed that. So here's the old critical source area concept of transport and source and management, and where those two overlap, that's a critical source area that we need to look at, because you have high transport, high source. The critical source area is where both occur, and you have the potential for P transport. So the first thing we want to do was we want to bring management front and center, because that's really how you control P losses. So we're going to bring that out as a separate circle, and we say, okay, where you have your management influences your high transport and your high source, that area is where we're losing phosphorus from. So let's control that area. But really, it's an additive process where we have that Venn diagram for runoff P, subsurface P, and particulate surface P. Okay? And then add the risk from each one of these, because really, for example, on the Lower Eastern Shore in a ditch-drained field, just the subsurface dominates, so we want these other two components to come out equal to 0, but you still could have very high risk just from this one component of subsurface loss. So your risk could be 100% just from subsurface. So that's how we change the math around. So this is what the new index looks like. Subsurface plus runoff plus particulate score equals your total score, and each pathway will have three components: management times source times transport. So each one of these components, surface, runoff, and particulate, will have a separate management, source, and transport factor that you'll have to calculate. The multiplicative nature of the index remains, but it's just now being done individually by transport pathway. You can significantly, one of the main changes that's come out of this, I think, is you can really reduce your score through management. What we did was we tried to include as many good management processes that we could in the index, and they all can decrease your score step by step. And so you can really bring down this score by doing some good management processes, because ultimately we want a tool like this to encourage the farmer to have better management in place to control loss. So, sediment P transport. We're going to use Russell. It's basically the same as under the old index. Basically Russell or Russell 2 times your soil test P times your management factor, which the only separate management factor we have is the combined distance buffer factor. I'll cover that in a second, because Russell really covers most of your management that controls sediment P. Things like tillage and all that stuff is already covered in Russell. So this is the distance buffer factor. And the way it works is, first you look at the distance from the edge of the field. This is much different than before. And then you get a factor. So if your P application is within 100 foot of surface water, you don't get any reduction. The value that goes in is 1, so your score doesn't go down. As you back away from the surface water, as the edge of the field moves away from the surface water, you decrease your score. If you're greater than 500 feet away from surface water, you decrease your sediment-bound P transport factor by 80%. So that's significant. And then we have, what is the ground cover between the edge of field? So what is this 500 feet covered by? And we have 50-foot riparian zone, permanent vegetative buffers, less than 35 or greater than 35 feet permanent vegetative buffer, and less than 35 feet vegetative buffer or no buffer. You don't get any reduction potential. So I want to cover what phosphorus saturation ratio is before I get into the other two sections. This is some data from published by Butler and Cole, Dr. Frank Cole, as many of you know, and his graduate student. Basically, we'll be using a predicted phosphorus saturation ratio. Currently, there are a couple of labs out there that are reporting phosphorus saturation ratio on their soil test report. And the other labs have said if there's a demand, they will report it. So, you're going to want to check with your lab if you're running a P index and see if they're going to provide this predicted PSR to you. But basically what PSR is the ratio of extractable phosphorus to iron and aluminum. Okay? And generally, greater than 25% saturation is considered, you exponentially increase your loss. What Dr. Cole shows here is dissolved reactive P in runoff or leachate on the y-axis and degree of saturation across the x-axis. And as you can see, as you get to 25%, it goes up. The other thing to notice is that for different soil types, it's different. And so, if your soil has more iron and aluminum, your degree of phosphorus saturation, will go up less, basically. So, this accounts for the iron and aluminum. It's more field specific, I think more accurate than just using soil tests alone for dissolved reactive phosphorus losses, which is what we're looking at in that surface runoff and subsurface loss formula. Craig is asking, will they be, I assume he means the soil testing labs, required to use the same formula? Yes. Yes, they already are. If you look, SFM 7, which is the extension document for the P index, is under review currently by external reviewers. And we provide the equation that is currently used for predicted degree of phosphorus saturation, because I don't want to get too bogged down in the details, but degree of phosphorus saturation, as presented here, originally was determined using an oxalate extraction, which no labs run. So Dr. Sims and Dr. Vadas, when they were at the University of Delaware, came up with a regression equation that predicts degree of phosphorus saturation from malic-3 phosphorus, iron, and aluminum. So right now, the University of Delaware lab reports this, and Agri Labs over on the Eastern Shore reports this, and they're using that equation that's published in a paper, and it's in the SFM7 extension document. When they run your soil, they're running malic-3 extraction on an ICP, and they easily can get back to phosphorus, iron, and aluminum. They plug those numbers in the equation, and they give you that saturation ratio that you can then just plug into your P index. So that'll be available out there. So here's the new factor for surface dissolved P. We have the transport factor, which is the same as in the old index for the runoff factor. The source now, instead of being soil test P, is soil phosphorus saturation ratio. And the amendment water extracted P, the same thing that was in the old index, that total P applied times the phosphorus solubility coefficient. And you can either have your phosphorus solubility coefficient determined by the equation in the extension document, or you can use the book value for the material that you're applying. This approach assumes that in the dissolved P component, the water extractable phosphorus in the soil and the manure are equally contributing, because you see it's half and half of the total source factor. That's basically the same way it was under the old index. And then, again, you have a management factor, and we have application method and timing factors. And then, again, that same combined distance buffer factor that I presented before for sediment P. Here's the application method factor. I'm not going to go into this in great detail, but basically, phosphorus application method factor for surface transport component. You would multiply the whole side by 0.8 if you surface applied after and surface applied, or waited 5 days to incorporate it over the winter months. And then that's kind of the max. You don't reduce your score very much there. We always figure that there's no such thing as 100% transport. So 0.8, 1 would mean 100% transport. 0.8 is 80%. That's kind of how the P-index has always been scaled, because we always figured that it's never 100% transport. So the worst case scenario here is 0.8. You can reduce your score by 40% by application from March to November, and less than 50% residue, or incorporated after 5 days. Now, all of a sudden, we can start really decreasing our score. If we incorporate within 5 days of application, or we have greater than equal to 50% residue, you decrease your score by 60%. You can decrease your P-index score by 60% by incorporating within 5 days. If you use subsurface placement or immediate full incorporation, so if I have an injector, if I have manure and I inject my dairy manure, I decrease my surface runoff P-index score by 80%. So no matter how bad things are for you as far as soil test P and transport, if you went and bought an injector, you'd probably be okay until your soil test just got so high it was unmanageable. So we've really tried to give management a real impact in this index. We are working to incorporate more management. This is a living document. As new tools become available, we'll be putting new tools in place. We actually, in the current draft that's under review, we have a tool that's not in the one that's currently under review, but is currently included in the draft I'm working with. And we hope by later this summer or in the fall to release this new draft. And it'll include the phosphorus ditch filters that we've designed and tested here at the University of Maryland. And so if you use a phosphorus ditch filter in a ditch drain system, you could reduce your subsurface transport factor by 60%. I see that I have a typo here on this slide. This is what happens when you type too fast. This should say subsurface dissolved P, not surface dissolved P. So you have your transport factor, which is a matrix of soil drainage class and hydrologic soil group. We have your soil source, which is the same as for the surface dissolved P. Here, your source is the same for surface dissolved P or subsurface dissolved P. Soil saturation and applied phosphorus. And then we have our management, but the management is different, because some things that are good for subsurface loss are bad for surface loss, and vice versa.
You took the buffer thing out of the subsurface, didn't you?
Yes, that's an important point, Paul. So this again is a typo. Combined distance buffer factor is not in the subsurface dissolved P loss. The distance buffer factor can't help you with subsurface loss because of the transport pathways being so connected when you have a ditch. So the first thing is, if you don't have artificial drainage, this factor is 0. You only run 1/3 of your index will be 0 if you do not have tile drains or ditches. Now, if you have a tile drain or a ditch, you've got to run this component, and you don't include distance in it. So here's the application methods for subsurface transport, surface applied, and subsurface placement without soil mixing. So even if I inject my manure, it doesn't help me if I'm not breaking up those macropores. I got to break up those macropores. So if I break up those macropores, now all of a sudden it starts to help me. If I incorporate it, excluding a straight aerator because we didn't think that gave much benefit in this situation, but if I incorporate it with extreme soil mixing, it can really help me because I'm deep mixing and I'm getting some low P soil mixed in with my manure. Yeah, I've got all kinds of comments streaming up here. Let me take a look at them. Is immediate incorporation equal to tilling the same day? Yes. If I have a high leachable soil and the manure is incorporated, does that increase the subsurface score? No, because if you mix it, it breaks the macropores. If you inject it without soil mixing, it just doesn't affect your score. You stay at the max level. What if drain tiles only drain 30% of the field? If drain tiles drain 30% of the field, you have to run the subsurface component. And, because you have that subsurface pathway, and that's your critical source area. That's where you have transport, and that's what the whole index is designed to find, that area where you have transport and source. So that's the overview of how you do the calculation for the P index. The summary is that P is vital for crop production, but repeated over-application has presented areas of environmental hazard. Most P export comes from a small portion of the watershed, really a small portion of the field, as the last question exemplified. A soil test threshold does not alone identify a high-risk area. So we use hydrology and management in the P index to assess that environmental risk. While I have your attention, I want to throw up that August 7th, 2013, we are having a Precision Ag Equipment Day at the Caroline County 4-H Park again this year. It'll be the third year we had it. It's a good time. Put it in your calendar. And I am on Twitter now. I'm trying to use this a lot for putting out information about soil fertility and nutrient management here in Maryland. I think it's become a pretty good tool. So if you're on Twitter, follow me at NPK Professor. Is moldboard plowing as effective as injecting? It is for decreasing subsurface loss. It significantly increases your surface particulate loss. So you have to look at your situation, your landscape. This is the good part of a P index. A P index is site specific. So if I moldboard plow, it will decrease my subsurface P score, but it would significantly increase my sediment bound score. And I would imagine the trade-off wouldn't be worth it. So ultimately, if you injected your manure with some soil mixing, a sweep or something like that, you would be in the best case scenario. You would end up with an extremely low P index score. Regardless of all the other factors, injection would give you a very low P index score from my assessment in some of the scenarios. I run some tests with the index, put different things in to see how it works. And, injection with subsurface mixing to break up those macropores would really reduce your score. So I'm opening this up for questions. We've got about 5 minutes left here for questions. So you can type them in there. I see Craig typing something now. I thought application of manure was going to not be allowed December through February. I believe that's the case, but our P index is really blind to policy. I wouldn't say blind. That's a bad way of putting it.
Well, for a couple more years, non-stackable can still be applied in winter.
Trish makes a good point. For a couple more years, non-stackable manure is still allowed to be applied in the winter. Nonetheless, our P index is made to last the test of time. If you're not allowed to do it because of some other rule, it's just like nitrogen management. If that P removal rate is above what your nitrogen-based plan allows, you still can't apply that rate. You're still limited by the state laws in regard to nitrogen application. Same with timing of application. If another law prohibits application from December through February, then you can't apply December through February. We just made our P index so that it was applicable if they decide to change that law in the future. Currently, you still can't apply. Maybe they decide to use this P index in, Montana, where they are allowed to apply in the winter. So, it's allowed. You don't have to worry about it if it's not allowed. A field that is adjacent to a ditch or stream needs to have a subsurface component. If there's no water to be found, no subsurface has to run or it will not affect the PMT score. So if I understand Craig's comment, yeah, if you have a ditch, so if you have ditch drainage or tile drainage, you have to run the subsurface. If you do not have that artificial component of drainage, you do not. Because Because where we get into trouble with subsurface transport is from the artificial connections to the shallow groundwater. And so a natural stream doesn't necessarily affect those flow pathways the same as cutting a ditch through a field, if I'm understanding Craig's comment correctly. How much of a ditch is a ditch? How much of a ditch is a ditch? This is a question I get all the time. I'm assuming you mean using a roto-ditcher or what's referred to as a temporary field lead. I got this question, honestly, on Monday at an event that we were doing. A ditch is defined as a permanent water conveyance, even if the flow in it is intermediate, I believe in SFM7. Am I quoting that correctly, Trish?
Oh, I believe so.
And so, you know, the devil's in the detail from a regulatory perspective, and really, this is a question for the regulator, and that's not me. But if it's temporary, that's not the definition we use in the P-index. If it's permanent, that's the definition we use in the P-index. So that's the threshold we set from the university's perspective. Moldboard plow to stop erosion loss? No, moldboard plowing would significantly increase erosion loss. So, because your transport potential would go up, even if you brought low P soil to the surface, you'd be moving so much more soil that you'd be moving a lot of phosphorus. So moldboard would never decrease your surface P loss. It could decrease your subsurface P loss. Other questions? I think
Craig asked about leaching, nothing a part anymore.
Soil leaching, not a factor in P movement. That's correct. We remove soil leaching as such a small component, and our subsurface component really captures it. Where our subsurface component is important, you might have some leaching in like a very deep, well-drained soil with huge macropores. It's such a small part of the landscape, we eliminate it for complexity's sake. We're trying to make it simpler and easier to run. Is that? My understanding is 3-year crop removal has got to be based on the nutrient management plan for the current crop and the next 2 years. That's what your planned crop removal is. One thing that we had discussed and might go to, I'm not sure how this would fit with the regulation, is to make it more simplistic, is to allow your previous 3 years crop removal. Because then you have yield records to rely on to prove and validate that was your crop removal over the last 3 years. But then you're limited. The next 2 years you cannot apply.
The other thing Newman